the software gives me a message that it's not recording audio, and that upsets me. Okay, so it is decreasing indeed on all its domain. So it's not increasing, but decreasing. Does it have an x-intercept?
No.
No, no x-intercept. Does it have a y-intercept?
Is it also 1?
Exactly, 0, 1. Excellent. Is it 1 to 1?
Yes.
Of course. Does it have an inverse?
Yes.
Yes, because it's 1 to 1. Okay, we're ready to graph it. So I'm just going to write underneath the graph just what is different. What is different is that the function is decreasing on negative infinity, infinity. Y equals 0 is a horizontal asymptote at positive infinity only. There is nothing else. It doesn't have an x-intercept. It has a y-intercept, which is the same. It's 1 to 1, and it has an inverse. So these are the only different ones. Decreasing, and the horizontal asymptote is at the other end. Okay, now we want to graph the inverse function. I have to graph y equals x first. And then I have to flip the graph with respect to y equals x. Of course, this point will be here. And this point is mandatory to be part of both, because you cannot reverse 1, 1. It's 1, 1. You cannot reverse 2, 2. It's 2, 2. So this point where the function crosses y equals x has to be part of both. And I have to graph a decreasing function. I'm graphing a decreasing function. This is F inverse. If you fold the graph, the entire graph, with respect to y equals x, this piece has to overlap over this one. This piece has to overlap over that one. They are symmetric with respect to y equals x. So this is decreasing. Another problem, the domain is 0 to infinity. So the inverse function, no matter what base, if it's base greater than 1 or if it's base less than 1, it doesn't matter. The inverse function will be a function with restrictions. Not the exponential, its inverse function. Okay. Any questions? I'm not going to name this function. We already know what it is because I mentioned that from the beginning of the title when we started. But we're not going to name it right now. We're not going to look at it. We're not going to analyze it. I just want you to have both graphs on the same coordinate system. Now, I would like us to work on some problems from this section. I have the book here open in the background if I'm not logged out. Okay, here it is. Okay, so we're looking at these graphs. I just want to discuss anything from 19 through 24. So we try to understand these graphs. They are only asking us to look at f of x, g of x, h of x, uppercase f of x, uppercase g of x, and uppercase h of x. Notice that this is the base function. They chose 3 to the x. Fine. Everything is extremely similar to 2 to the x. But then they are throwing some transformations in there. So let's start with one by one. We're trying to understand this exponential function better. Okay, so let me copy f of x equals 3 to the x, g of x equals 3 to x minus 1, h of x equals 3 to the x and minus 1, uppercase f of x is negative 3 to the x, g of x equals 3 to negative x, and finally negative 3 to negative x. Okay. Good. How do I graph this? Well, I know how to graph it. It's an exponential function with a base greater than 1. Nice and easy. No problem. Crossing at 0, 1. That I know. Now, let's analyze this graph. What transformation is this on the base function when we change x into x minus 1? This is a good review of transformations. What happens when we change x to x minus 1? What happens to the graph? Anyone remembers? What happens to the graph when we change x to x minus 1? This is a good review for the final as well, right?
Will it move to the right?
Exactly. It will move to the right one. Very good. So this point moves here. This graph is 3 to x minus 1. Excellent. Perfect. I'm not going to graph the base function again because I don't want to put too many graphs on there. So we're looking at this one next. But first I want to graph the base function. So this is the base function, 3 to the x. Can anyone tell us what is the horizontal asymptote of this graph? Again?
0.
Yes, y equals 0 is a horizontal asymptote. You'll see in a moment why I'm asking. Now, let's look at this function. 3 to the x, but then minus 1. Not x minus 1, but y minus 1. What happens to the graph now?
It will go down.
Indeed. But that's the reason why I asked you what is the horizontal asymptote. Because first I have to move the horizontal asymptote 1 down. This function no longer has y equals 0, the horizontal asymptote, but y equals negative 1. And now I will move the graph. So from here at 0, 1, it will move here at 0, 0. So this is 3 to the x, and then minus 1. Good. The next one, I will graph again, because I don't want to put too many graphs in there. So here's, again, 3 to the x, crossing at 0, 1. Now, what happens here? So we had 3 to the x, but now we have negative 3 to the x. What transformation is this when we multiply the y value by a negative number? In this case,
Reflection.
yes, it reflects with respect to the axis. So this point is here now as a reflection. Very good. Negative 3 to the x. Okay, 2 more. G of x. I graph again. So this is 3 to the x again. Now you're going to dream about 3 to the x. We graphed it so many times. So now I'm changing x to the opposite of x. So this was x, but now negative x. So when we had y, and then negative y. Now we have x and negative x. What will this be then? From x to negative x. From
So
x,
it will flip over onto,
the y-axis, yes, indeed. So this is 3 to negative x, because it's 1/3 to the x power. And we know that 1/3 to the x power is a decreasing function. This is what this means. 3 to negative x is 1/3 to the x power. Okay, finally the last one. Notice that this has two transformations. We already graphed 3 to negative x. Now this is a transformation on G. What transformation is this? When I have a y value, and then I multiply the y value by -1. What happens to the orange graph? We're multiplying the orange graph, or the y values, of course, by -1. What will happen?
it will be another reflection.
Another reflection, and this is it. So this graph is -3 to negative x. So this was a good exercise to review our transformations from chapter 2 and apply them to something that we just learned today. Exponential function with a base greater than 1. Okay, I would like to look at some word problems. So we can identify them from here. We already graphed all of them. Okay, I mean, we could go and choose. Now, what I disagree with, for example, there is no horizontal asymptote here. No. If you remember, every time we graph functions with asymptotes, we have to graph the asymptotes first. So the horizontal asymptote is missing here. I disagree with that. Okay, so let's do look at some applications. So here's one application. These are two formulas, the compound interest formula, meaning when the interest is compounded or recalculated, basically, n times per year. I'm going to write these formulas down for you. But this one is a different compound interest formula. It's continuously compounded interest. Okay? So here the interest is compounded continuously. So let me explain these formulas, and then we'll look at word problems. So when we deposit money in a bank, they should be giving us, so this is page 5, is it 5? Yes, it's 5. So compound interest. Two different types. N times per year and continuously compounded interest. The formula here is A equals P 1 plus R over N to NT. I'll explain each piece in a moment. And here A equals P E to RT. And let's go through each and every component. A is the accumulated value. Let's say we deposit the principal, P, P is what we deposit today, and A is what we get in T number of years. The accumulated value and the principal. The principal we deposit today, we open an account, we deposit the principal, and the accumulated value is what we end up with T years from today. R is the annual interest rate. T, time in years. Of course, E, I didn't mention that. It's called the Euler's number. What does Euler number mean? Here it is. So if you want just E to see it, second with division symbol and press enter, and it will give you 2, 4, 6, 9 digits of E. E is this number. It was so-called discovered, if you want, by Euler, and that's why it appears in real life situations many times. You'll see in many applications. We're going to work with this in a moment. And because he discovered it, he showed that it repeats itself so many times in different situations. It bears its name in the sense that it's denoted by E. So this is Euler's number, which is the same with the base of the natural exponential function that we just discussed. The same thing. But if you want just E with no power, meaning power 1, then you just use second and the division symbol, and you get an approximation for Euler's number. Okay, so this is the base of the exponential function. Accumulated value, principal the same, annual interest rate, and T, time in years. They're all the same. So now let's look at our problem. Let's choose a problem and go through all these steps. So let's read. They're all pretty much similar. Find the accumulated value of an investment of such and such, 5 years at the interest rate of this, if the money is compounded semi-annually, which means twice a year. Compounded quarterly, we have 4 quarters in a year. Compounded monthly, we have 12 months in a year. And compounded continuously, I can no longer use this formula. I have to use this one. So they are all the same, pretty much. So please choose one. Okay, very good. So let's look at problem 54. So let's read it. Find the accumulated value of an investment of 5,000. That is the principal. The principal we're given is 5,000 for 10 years. That is little t. T equals 10 years at an interest rate, that's lowercase r, 1.56%. We cannot use percent. I have to change it into a decimal number. So I have to move the decimal digit 2 spots to the left, 0.0156. We do not use percent in the formulas. Okay, back to the problem. If the money is compounded semi-annually, so part A, n equals 2. Part B, compounded quarterly. In B, n equals 4. And C, monthly, n equals 12. And in part D, continuously. Okay. Very good. So for the first 3 parts, I have accumulated value equals the principal 1 plus the annual interest rate divided by n raised to nt. Notice that n can be 2, 4, and 12. I highly recommend writing the following function. A, replacing P by 5,000, 1 plus R by 0.0156, and N, because it changes from 2 to 4 to 12, I'm going to write X for a moment. T is 10 years, so the power is 10x. Why am I doing this? It's because I don't want to repeat the calculation 3 times. I just want you to follow my thought in a moment so you'll understand what I'm trying to do. So in y equals, clear everything you have, and I'm going to enter 5,000, open the parenthesis, 1 plus 0.156, 156 divided by x, close the parenthesis, power, and I like parentheses, 10x. So I entered the function, and all I need to do now is with the second and table, and I enter my 2, 4, and 12. I don't want to repeat this process and potentially make a mistake. I entered the function. So then I read A of 2 is 5840.59. Scroll further down. A of 4 is 5842.36. And scroll further down so I can see all the digits. A of 12 equals 5843.54. By entering this function, because realizing that this changes, so I denoted this by x. And once I entered this function, it took me a blink to replace this by 2, then replace it by 4, and then replace it by 12, and get all these numbers in a blink. Not repeat the whole thing 3 times. Of course, you're going to get the same answer, but you will work much harder. And this is really not what you should do. Now for part D, however, I have A equals PE to RT. So I have A equals 5,000 E to R, which is 0.0156 multiplied by 10. This does not need me to create a function. I'll stop in a second. I'll finish with this and I'll stop. So get out of there and just enter 5,000 and then E, and in parentheses you can multiply by 10 or just put in parentheses 0.0156 multiplied by 10 and close, and I got A equals 5844.13. So if the interest is recalculated every second continuously for 10 years, we get, of course, the largest amount, but they're all extremely close. Extremely close. So this is compounded twice and recalculated twice per year. This is recalculated 4 times and put back in. And this is 12 times a year, a little bit more, and continuously is the maximum. Okay, I'll stop for 10 minutes, promise.